开始。
Hi, I'm Chi from Group 6. Today we're going to present our work on improving EKF-based GNSS-INS integrated navigation system through some advanced method. Our team has implemented three novel algorithms, IEKF, IgG3, and KGP, to enhance positioning accuracy and system reliability, addressing the limitation of EKF. This presentation will unpack these methodologies, our experimental process, and the impactful result that set the stage for future exploration. We'll cover four essential sections that frame our discussion: motivation, methodology, results and analysis, and finally draw conclusion. Let's begin the first part. As we know, EKF not perform well when observations are not reliable and cannot adapt to dynamic measurement noise. To fix this, we introduce KGP for EKF when observations are not reliable, even not available. And we introduce a IgG3-based IEKF method to deal with this dynamic measurement noise. Next section is about methodology. KGP stands for Common Featuring-Based Gradient Boosting Decision Tree using particle swarm optimization. KGP is a model that can help IMU compensate the planar position when the GPS data is not available. When GPS data available, KGP trains with sample from IMU, labeled of reliable position for common filtering. When GPS data is not available, KGP uses a model to predict the error of IMU and compensate that error. GBDT is a kind of regression decision tree. When training the data, GBDT have multiple hyperparameters. Thus, we introduce the particle swarm optimization to optimize the hyperparameter of GBDT. PSO is an optimization algorithm that considers both personal and global best particles for GBDT. And for KF-Gene's model, firstly, I'd like to acknowledge the team of Professor Xiaojin Niu of the Integrated and Intelligence Navigation I2NAV group from GNSS Research Center of Wuhan University for providing the open source KF-Gene software that were used in this paper. KF-Genes is an open source software in C++. It's a high precision EKF loose coupling system for GNSS observation and IMU record. We ported the code from C++ to the Python for further development of machine learning algorithm like KGP. KF-Genes uses geodesy knowledge when changing the coordinate system, and this package can also be found on the GitHub. For more information about KF-Genes, please visit their website. The state vector is defined as IMU position and velocity arrow, attitude arrow, gyroscope, and accelerometer biases and scaling factor of gyroscope and accelerometer. The picture on the right side indicates how our three functions are implemented based on KF-Genes.
So the IEKF, which is short for Innovation-Based Adaptive Estimation common filter, relies on the dynamic evaluation of the innovation covariance metrics rather than the traditional calculation to cope with the abrupt noise brought by the sensors. By applying maximum likelihood estimation to the Gaussian distribution of the innovation vectors, an optimal estimation is obtained after some arithmetic operations, which is exactly the average of the square of innovation vectors within a sampling window time. However, the IE may disrupt the system as assumptions are largely made upon linearity. Thus, we need the IgG3 to help us further. The IgG3 tries to further increase the robustness of the system by dynamically selecting the sliding window length. And this is done by comparing the innovation square over the last innovation covariance metrics with the chi-square values as thresholds. Thus, three cases are divided. When the value is smaller than the lower threshold, the situation is considered to be normal. And when the value is between two thresholds, which the thresholds are said to be very close to each other, the situation is regarded as under slight changes and fluctuations, and thus the system needs some small adjustment. When the value is larger than the larger threshold of the system, it is considered to be no longer valid, and thus we need to minimize the influence of the innovation by including only the last square of innovation vectors. So here is the overall workflow of our project. We firstly initialize the EKF and KF GenFs. We do the normal propagation of the EKF position state parameters, and then we use IgG3 to decide the sliding window n as a sliding window length for the IE. After IE, we have an adaptive SK, which is the innovation vector covariance, and we use that to calculate camera filter gain to update the state parameters. During this process, the state parameters will be recorded into a dataset for the KGP. If the KGP collects sufficient data after many runs, it will have enough points to build a model, and then the KGP will fit that model and use that model to compensate the future position estimation with IgG3 being turned off at the same time. Also, when the limit time step is achieved, we will consider that the features are changed, and thus we will have to clear up all the data of the KGP and iterate this whole process all over again.
Next, I'll talk about our experiments and result results. We use existing dataset for the experiments, which is provided by IQNAV group of Wuhan University. The dataset consists of GNSS, RTK, and IMU from open sky industrial area, and a ground truth dataset, sufficient for our testing. As a result of the estimation, we clearly see that the algorithm can correctly predict the general tendency of the data. A comparison of the ground truth and estimation using our algorithm is given, and no obvious difference is observed. We can tell there's a better performance in trying to maintain the gyroscope X-bias. The instability caused by G3 and IE is largely mitigated, and a better overall smaller scaling factor and bias are presented. A larger drift is seen in Y and Z axis, which implies a potential and better tuning. As for accelerometers, similar tendency can be told as well. We can also compare the standard deviation of navigation result. We can clearly see that our method reduces the standard deviation and mitigate largely the insufficiency of robustness.
Now I will give a conclusion. Here are our contributions. We introduced the IgG3 IAGKF and the KGP to the project. We put existing EKF framework from C++ into Python. And here are some limitations. KGP have some limitations such as the complexity and the computational load. It has the convergence issues, and it needs the high quality of the data. And the IAGKF limits on convergence speed, tuning, and parameter sensitivity. It also has the risk of divergence. Finally, for the IgG3, it limits on computational intensity, complexity of tuning, and scalability. Finally, for our future work, we can using machine learning to tune the parameters. Second, we can develop more robust method for this system. Finally, we can do some work on error modeling and mitigation. Finally, thanks to Dr. Xiaojun Liu from Wuhan University for providing the dataset that was used in his paper. That's all. Thank you.